Hello everyone, I'm Lijie Chen from MIT. Today I'm going to talk about the quest for superfast derandomization. This talk is based on joint work with Lijie Chen. Here is the plan for today's talk. I'll begin by introducing the concept of derandomization and discuss why people are interested in that. Then I will go over some previous work and also discuss some recent developments. In the second part, I will try to give some intuitions on the techniques behind the results. So let's get started. So first, as you may already know, randomized algorithms are algorithms that make coin tosses during this computation, and they are expected to be correct with high probability over the coin toss, instead of being always correct. Randomized algorithms are very powerful, and it has been playing an essential role throughout computer science. Famous examples of randomized algorithms include quicksort algorithm for sorting numbers, Miller-Rabin primality test for testing whether a number is a prime, hashing for checking whether two strings are identical, and stochastic gradient descent for machine learning, and also the problem of generating an n-bit prime. For the problem of generating an n-bit prime, a simple randomized algorithm can just keep generating n-bit integers until it hits a prime. One can show this takes polynomial time with high probability. For more examples, there is a famous book on randomized algorithms containing dozens of important randomized algorithms and their applications. So what does derandomization mean? As the name suggests, the process of derandomization asks us to convert a given randomized algorithm into an equivalent deterministic algorithm solving the same task, which does not use any randomness. More formally, we are asking that given a T of n time randomized algorithm, T of n measures the running time of this randomized algorithm on n-bit inputs. What is the fastest running time of an equivalent deterministic algorithm? In other words, what is the fastest derandomization of the complexity class BP times T of n? We use BP times T of n to denote all problems solvable in randomized T of n time. There are two important types of problems one may be interested in. The first is decision problem, in which the answer is either yes or no. For example, deciding whether the given integer is a prime or not. This is a decision problem. The second type of problem is search problem, in which one wants to find a particular object satisfying certain constraints. For example, the problem of generating an n-bit prime is a search problem. Another example is that you are given a formula and you want to output a satisfying alignment. This is also a search problem. We'll mainly be focusing on derandomization of randomized algorithms solving search problems, but most of the results discussed in this talk will equally apply to derandomizing search algorithm as well. But for simplicity, we'll just focus on talking about decision problems. So now we know what is the goal of derandomization. But why people care about making randomized algorithms deterministic? What is the advantage of deterministic algorithm over randomized algorithm? First, we'll begin with some practical implications of randomization. We know that randomized algorithms require perfectly uniform random bits to treat them as coin tosses. This sometimes could be a scarce resource because maybe you don't have access to those perfectly random bits. Your random bits could be biased, and in that case, your algorithm may not behave correctly. That will be an issue. Second, randomized algorithms may still make mistakes, despite with very small probability. In certain important situations, one may want to completely eliminate potential error. In that case, because deterministic algorithms are always correct and never make mistakes, it makes them more preferable than randomized algorithms in those situations. Finally, since deterministic algorithms do not involve randomness, they would always have a fixed output on a given input, while randomized algorithms may give different outputs when it's run by different people. This lack of reproducibility may be a serious issue in certain situations. For example, recall the randomized algorithm for generating n-bit primes before. Since we are essentially guessing random n-bit integers and check them, different people running this algorithm would output different primes. And this can be a big issue in many settings because we cannot use this algorithm to agree on a particular prime. But for a deterministic algorithm, every run will give you the same prime, which is a big advantage in many settings. From the theory side, randomness and determination is connected to many different areas in theoretical computer science. This concept and methodology has also been very influential. The study of determination has led to many interesting discoveries in theoretical computer science, so it's very interesting from a theory perspective. I also want to highlight one particular connection between derandomization and the circular lower bounds. Proving circular lower bounds is one of the most important questions in complexity theory. It is also one of the hardest questions that we don't really have much progress in many years. Several classical work has demonstrated that there are two-way connections between the task of derandomization and the circular lower bounds. Namely, proving strong circular lower bounds would imply fast derandomization for all randomized algorithms. And on the other side, fast derandomization would also imply circular lower bounds, which we have no idea how to prove. Hence, the study of derandomization is tightly connected to the important task of proving circular lower bounds. This also adds to the theoretical importance of the study of derandomization. So now we are ready to discuss previous work on this topic and also some recent developments. The most important discovery in the field of derandomization is the surprising connection between hardness and randomness. In particular, a line of classical work shows that if certain functions are hard to compute, then all randomized algorithms can be derandomized efficiently. I will explain what exactly means by hard to compute later, but the message here is that we do believe certain functions are very hard to compute. For example, we believe that all NP complete problems shouldn't have polynomial time algorithms. We also believe the problem of factorizing an integer is probably hard, and this is one of the foundations of modern crypto. So, although these two concepts, the existence of hard functions and determination, seem to be very different, they are indeed tightly connected. Under some plausible hardness assumptions, the classical work by PRGS and Wijsen showed that a T of n time randomized algorithm can be derandomized to an equivalent T of n to the c time deterministic algorithm for a constancy, which is at least 7. This is a super important result as it implies that problems solvable by polynomial time randomized algorithms are also solvable by polynomial time deterministic algorithms. That is, if we only care about whether a problem can be solved in polynomial time or not, then we are already done with this question. Still, the resulting polynomial time algorithm is not very relevant for the practice, as the T of n to the 7 running time is probably too slow for most potential application. So this calls for a natural question that whether we can further improve this running time, like we want to bring down this constant 7 to maybe 1 or 2. In a recent breakthrough, Doran, Moshkowitz, O, and Zuckerman proved that under stronger hardness assumptions, one can significantly improve the derandomization overhead. In particular, one can convert a T of n time randomized algorithm into an equivalent deterministic algorithm of T of n squared running time. This is very impressive as quadratic running time is much faster than T of n to the 7. This also opens the possibility that maybe we can reduce the running time even further from quadratic to, say, almost T of n. In a recent work by Chen and Tiao, we answered this question in the affirmative by showing that under plausible hardness assumptions, one can derandomize a T of n time randomized algorithm with an overhead of roughly n. So recall n is the input length. Moreover, perhaps surprisingly, we show that under certain plausible conjectures, this overhead n is in fact optimal. This optimality result is for a natural problem called polynomial identity testing. But unfortunately, we don't have time to go into details of this problem because it's a bit complicated. But roughly speaking, the problem gives you two graphs representing two multi-variable polynomials. And the goal is to determine whether these two graphs compute the same polynomial or not. For example, these two graphs on the slide, although they look different, they indeed compute the same polynomial x1 plus x2 squared. So we show that under certain hypotheses, this polynomial identity testing problem has a T of n time randomized algorithm, but cannot be derandomized with an overhead less than n. So it seems we are hitting a barrier as we cannot get faster derandomization for at least some problems. But perhaps we can relax our requirements a little bit to get something faster. Recall that previously we required the deterministic algorithm to agree with the randomized algorithm on all possible n-bit inputs. Perhaps we can relax that by allowing the deterministic algorithm to make some error on some inputs. So in particular, we have an important lesson from crypto, saying that if two things are indistinguishable by polynomial time algorithms, then they are practically the same. So inspired by this observation, can we show randomness is indistinguishable from useless? In other words, can we show that BP times T of n is effectively times T of n times n to the little o1. So formally, the goal is that for every problem computable by randomized T of n time algorithms, we want to find an T of n times n to the little o1 times deterministic algorithm D sub L, such that no polynomial time algorithm can find a mistake, meaning an input x such that L and D sub L differs with at least 1 over polynomial probability. In other words, there's no feasible way to find a mistake of all derandomization with non-negligible probability. This is a very strong guarantee as it basically says that although all derandomization could make some mistake, that no polynomial time algorithm can find such a mistake. Hence, practically speaking, no polynomial time adversary can break this derandomization by finding a mistake, which is already enough for most of the practical situations. In the most recent work by Chen and Tiao, we show that under some plausible hardness assumptions, one can in fact show BP times T of n can be derandomized to effective times T of n times n to the little o1, meaning that one can achieve a generalization with almost no overhead, such that no polynomial time adversary can find a mistake. We remark that this result requires a new framework for Hardness-to-Randomness, but due to the time constraint, we will not get into that during this talk. So you are welcome to check the paper. So now let us clarify what does it mean by certain functions are hard to compute. Recall that previously we have such an intriguing connection between hardness and randomness. By hard to compute, we mean that certain functions cannot be computed by fast, non-uniform algorithms. So now we need to introduce the concept of non-uniform algorithms. It's also called circuits in many textbooks, but here we'll just use the term non-uniform algorithms as it's more intuitive than circuits. In more detail, usually by algorithms we mean uniform algorithms, which is a piece of program with fixed length, and this program is supposed to solve the problem for all possible input lengths. So for example, consider the famous algorithm of depth first search. This algorithm has a fixed description of several lines, but it can be applied to graphs of all possible sizes. For example, 100 vertex graphs, 1,000, 10,000, even 10 to the 100 vertex graph. We are all using the same code, the same program to solve this problem. On the other hand, a non-uniform algorithm can use longer program for longer inputs. For example, in a non-uniform algorithm, one may use code of 100 bits to solve the problem on 100 vertex graphs. But we can also use much longer programs to solve the problem on much larger graphs. So the size of the program can grow with the size of the input. The running time of the whole non-uniform algorithm on a certain input length will be measured as the worst case execution time of this particular program plus the length of the program. Because now the length of the program is not fixed anymore. It could grow with the input length. So now we are ready to specify the hardness assumption in classical work. This so-called plausible hardness assumption is in fact saying that exists a function f computable by uniform algorithms in 2 to the n time, but not by non-uniform algorithms in 2 to the 0.01 n time. In other words, we are saying that exists a problem f such that we have a single program of fixed size which can solve this problem in 2 to the n time for all input lengths. But even if we are allowed to use longer program on longer input lengths, we still cannot solve this faster than 2 to the 0.01 n time. Another interpretation of this hardness is saying that no preprocessing can significantly reduce the hardness of the problem f, meaning that even if we can spend an unbounded time to do some preprocessing to produce a fast program for f, this fast program still cannot be faster than 2 to the 0.01 n time to solve f on all n-bit inputs. The hardness assumption in the DMOZ paper or the CT paper are also hardness against non-uniform algorithms. But these assumptions are stronger since they are aiming for a much faster generalization. Finally, let's summarize all the results we mentioned. The classical work achieved a polynomial time generalization but with a huge exponent. The work by DMOZ improved that to quadratic overhead. And the work by CT improved its overhead from quadratic to n. And in another recent work, it showed that this overhead of n is in fact optimal under certain hypotheses. Finally, in the most recent work, Chen and Tell showed that if we only want a derandomization such that no polynomial time algorithm can find a mistake, then one can in fact derandomize T of n time randomized algorithm with almost no overhead, and such derandomization may already be enough for most of the situations. Next, we'll talk a bit about the proof techniques behind all these derandomization results. We begin by introducing the concept of pseudorandom generators, or PRGs. Formally, a PRG is a deterministic procedure which expands a short seed of length s into a longer output which looks uniform to polynomial time procedure on t-bit random input. By looks uniform, we mean that the acceptance probability of the given procedure over the uniform distribution is close to the acceptance probability of the same procedure but given the output distribution of G instead. By the output distribution of G, we mean that we feed G with the s-bit uniform distribution and we look at the output distribution of G. If this is the case, then we can use the acceptance probability of A over the output distribution of G to estimate the acceptance probability of A over the uniform distribution. In particular, one can first obtain all outputs of G in 2 to the s times T sub G time, where T sub G is the running time of G. Then we can feed all these outputs as randomness to the algorithm A to obtain the estimation of the red box. Because the estimation in the red box is close to the actual probability over the uniform distribution, this gives us a deterministic algorithm for simulating A in 2 to the s times T plus T sub G time. So 2 to the s is required to enumerate all possible outputs for G because there are s-bit of inputs to G. So that total 2 to the s possibility for input to G. So now we understood the relationship between the running time of the derandomization and the parameters of the PRG in terms of the seed length s and its running time T sub G. So we are ready to discuss the bottleneck in previous derandomization results. For the classical work by Implagazzo and Wijesen, the bottleneck there is that both the seed length and the running time of the generator G is pretty large, which results in the huge polynomial time overhead. In the more recent work by DMOZ, the bottleneck there is mostly on the seed length, since their seed length is at least log T of n, and plug that into the formula for running time. This gives us at least T of n squared running time as a result. Recall that we are aiming to get an overhead of roughly n. To achieve this, we would require the seed length to be roughly log n, and the running time of the generator to be roughly the same as the running time of the algorithm T. So we have two requirements for our approach to work. So we'll first be discussing the seed length. Formally, we have an algorithm A such that the algorithm A first takes an n-bit input and then take t bits of randomness. And the requirement is that if the answer for x is yes, then the acceptance probability of A on x is at least 9/10. Otherwise, it's at most 1/10. We claim that there exists L equals all n many t-bit strings y1, y2 to yl, such that for all possible n-bit input x, the following holds. That is, if the answer for x is yes, then over the uniform distribution of all the yi's, the acceptance probability of A is at least 2/3. Otherwise, it's at most 1/3. Therefore, one can actually enumerate all possible yi's to determine whether x is yes or no. In particular, we have a pseudorandom generator G, which maps from integer I to string y sub I. G is a valid PRG with seed length log L equals log n plus O1. The seed length is log L because it takes log L bits to describe an integer from 1 to L. So this is the claim we want to prove. And now let's show how to prove such a claim. In particular, this means that there exists a PRG of log n seed length. The proof is in fact very simple. First, we'll let L to be a big constant C times n. Then we pick L t-bit strings y1 to yl at uniformly random, and they are all independent. Next, we can apply the Chernoff bound to show that for a fixed input x with probability at least 1 minus 2 to minus omega L, the acceptance probability over the uniform distribution and the acceptance probability over all these yi's on this input x differ by at most 1/10. This is a simple application of the Chernoff bound. Furthermore, by another application of the union bound, and note that L is some big constant times n. In particular, we can choose C to be large enough such that 2 to the omega L is greater than 2 to the n. Then we can show with probability greater than 0 for all input x, the acceptance probability over the uniform distribution and the acceptance probability over all these yi's differ by at most 1/10. In particular, now this union bound implies that for all n-bit input x, if the answer is yes, then because it differs with 9 times by 1/10, it's at least 2/3. Otherwise, because it differs by 1/10 by at most 1/10, it's at most 1/3. Therefore, we finish the proof of this claim. So to conclude, there exists log n seed PRG fooling t time randomized with n-bit inputs. Of course, our goal here is to find an explicit algorithm generate such a PRG. We also remark that one can also show that log n seed length is also necessary for fooling t-time algorithms with n-bit inputs. Therefore, at least non-uniformly speaking, log n seed length is both sufficient and necessary. In the rest of the talk, we will not discuss the details on how to achieve log n seed PRGs, but I think the most important message here is that it's possible to achieve log n seed, and they actually exist. So we'll achieve them via some technical work, but we'll not get into that in detail of this talk due to time constraints. So now let's talk about the constraint on the running time of G. For this, we have to explain some details about the hardness-to-randomness paradigm. So the idea here is that we start with a hard function f, and we then use it to construct a PRG g to the f, which is based on the hard function f. The goal is to prove that g to the f follows randomized algorithms based on the hardness of f. In other words, if f is hard, then g to the f can be used to derandomize those algorithms, as we saw before. So how can we prove such a conditional statement? It seems these two parts, like fooling randomized algorithm and hardness of f, seems not very connected. The most important idea here is to consider the contrapositive. In other words, we'll prove that if g to the f does not follow one particular algorithm A as some input, then one can use this algorithm A to construct a fast algorithm R to the A, which can compute f. This will imply what we want, because we assumed f cannot be computed by fast procedure. Hence, g to the f must follow our low running time algorithm A, as otherwise the reconstruction will give us a fast procedure for f, but which is a contradiction based on our assumed hardness for f. The best part of this approach is that instead of proving g to the f follows our low running time algorithm A, which seems not clear how to prove that directly, we switch the perspective, and we switch to the problem of constructing a fast procedure to compute the hard function f given the algorithm A. This in principle is an algorithmic challenge, so it's easier to do it. So now we are ready to explain how this approach is implemented in previous work and why it brings a huge overhead there. So to recall, some previous work give us a pretty large polynomial derandomization of T of n time randomized algorithm. The reason is that, in particular, in the classical work, which gives us a huge polynomial overhead, the corresponding reconstruction also gives a huge overhead. What I mean is that, given a T of n time algorithm which is not followed by g to the f, one can obtain a t to the c time fast procedure computing f. But here the exponent c is a large constant at least 7. So take the contrapositive. This would imply that, as discussed before, if f cannot be computed efficiently in t to the c time, then it will imply g to the f follows t time algorithm A. But the catch here is that because we need to assume f is hard at least for t to the c time algorithm, this means that g to the f, which is based on f, also takes at least t to the c time to compute. Hence, the running time of t sub g is at least t to the c. So let's look at the requirements before. We remember that we want the seed length to be log n and the running time of the PRGG to be close to t. Hence, the huge reconstruction here is a serious problem for us to obtain fast determination based on the hardness of f, because this huge reconstruction overhead force us to choose a hard function f, which is hard for t to the c time, but this will imply g will also require t to the c time to compute. To overcome this issue, the most important new technical part of this new work is to obtain a very efficient reconstruction. In particular, we will first assume one-way function exists. One-way function is a certain object from crypto, and its existence is widely believed by the crypto community. In particular, we'll construct a generator G to the F, which will expand log n bit input to T bit output. The key part here is that given a T-time algorithm which is not fooled by G to the F, one can obtain a fast procedure R to the A such that which computes F in T times n to the little o1 time. So by taking the contrapositive, this implies that if F cannot be computed efficiently in T times n to the little o1 time, then G to the F will fool all possible T-time algorithms. The most important consequence here is that it's now possible for F to be computable in T times n to the 0.01 time. In particular, this means G to the F can also be computed roughly in T times n to the 0.01 time. Recall that the running time of the overall randomization is 2 to the S times T plus T sub G. So now our new generator has precedence log n, and the running time of T sub G is improved to T times n to the 0.01. So putting everything together, we obtain a randomization in T times n to the 1.01 time. Finally, we mentioned a bonus result on the right assumptions for derandomization. So in a recent paper by Chen and Tell, we give a new Hardness-to-Randomness framework for non-black box derandomization based on new uniform hardness assumptions. Recall that in classical work, we have to assume hardness against non-uniform algorithms to get derandomization. So in this work, we show a new type of uniform hardness assumption, which is both necessary and sufficient for derandomization. That is, for these new uniform assumptions, we have two-way implications between this assumption, from this assumption to polynomial overhead derandomization, and from polynomial overhead derandomization to this new assumption. As we discussed before, previous Hardness-to-Randomness frameworks are based on PRGs. In particular, from some non-uniform lower bounds, one can get all log n seed PRGs for polynomial time computation. And this log n seed PRGs implies polynomial overhead derandomization. So that's the classical result. But the point is that it's unclear whether polynomial overhead derandomization implies log n seed PRGs as well. So maybe the assumptions here on non-uniform lower bounds are too strong because it does not seem to be equivalent to derandomization. On the other hand, one can conjecture some uniform lower bounds, like exponential time does not equal to randomized polynomial time. From such hardness assumptions against uniform algorithms, one can obtain PRGs that work on average, meaning that the PRG will successfully derandomize algorithms on most of the inputs. Such a PRG is implied by polynomial time overhead derandomization, but does not seem to imply worst-case derandomization because the PRG only works on most of the inputs. So here the assumption seems too weak because it does not imply what we want. So in this new work, we introduce new types of hardness assumptions, which will both imply polynomial overhead derandomization and also is implied by polynomial time overhead derandomization. and all new construction is based on targeted PRGs instead of PRGs. I don't have time to define what it means by targeted PRG, so you are welcome to check the paper. Finally, if you are interested in this topic and want to learn more, there are many interesting further readings on this topic, and you are welcome to check out these papers. Thanks so much for your listening.